Good afternoon. So this is week number 06, week 6. We are in lecture B. So it's Wednesday. We are going to focus on Kalman decomposition. This is a very important foundation for us to understand the structure of state space, and its subspaces. Okay, so, and this is also the foundation for us for learn many different types of standard forms. Like controllability, controllable form, observable form, and so on and so forth. So different forms, okay? And these forms will be useful for us to discuss the control problem. So we're not there yet. So here's the plan. So in week 7, that's next week, we are going to cover realization. And we're going to talk about minimum realization, balanced realization, and so on and so forth. Okay? And 8, 9, 10 is our spring break. So we are going to basically focusing on the state feedback control will start from week 10. Oh, sorry, week 11. This 10, this is 11. So 10 is missing, and then week 11. So we are only here to do control, but here we are going to do stability. Okay. So you can see we did stability very late. I think this is an advantage for us to have a solid foundation on all the fundamentals before we even touch the stability. I like it. Okay. This is something new in the sequence of learning. So I hope you know where we are. Then we're going to interesting. So I put PS5. Looks like every week we're going to have a 1 hour tutorial session, help session. So please budget the time, next 2 weeks, 3 weeks maybe. So I'll give you a take-home exam on week 10. But before here we do stability, then we do state feedback, we do observer-based, OBS, observer-based control, full observer, full order observer, and reduced order observer. Okay? Then LQR. Okay? LQR. I hope to cover LQG. I hope I can cover Pontryagin maximum maximum principle. Okay? Pontryagin maximum principle. Pontryagin's maximum principle. So hopefully I'll have time to show you optimal control problem. So we'll see if our time allows. But today, before we go to Kalman decomposition, is also called canonical decomposition. So let's remember what we learned about discrete time reachability. Okay, I think we briefly reviewed differences between reachability. Reachability means you need to be able to reach out. Okay, reach out. What's the reach out? So you start from here. You reach out. Okay. So then Can you reach out? Can you go anywhere you want? Is the reachable space is Rn? I don't know. Yeah. That's one thing. It's called reachability. Another thing is you are already here. Okay, you are already here. Okay. So I hope you will be able to get to the origin. Okay. So whenever you go there, you can always return back to the origin. So many people say reachability and controllability are the same. Controllability are the same. Okay? So I agree with you. If, I don't know if it is continuous time LTI, LTV system, continuous time LTV or LTI system. Okay? So these are the same. Okay? However, for discrete time system, this could be different. Okay? For discrete time system, this could be different. So that's why you don't hear the reachability very often. Okay? I uploaded 2 files in our week 6 files. So please go through that. There is an explicit question. What's the difference between reachability and controllability? The answer is 0 if it is continuous time. They are the same. But in discrete time, no, they are not 0. There is a difference. So for discrete time system, we talk about reachability. You need that kind of a reachability matrix. Okay, that is defined as a B, phi B, and phi B from K0, Kf, that way. And remember that we are talking about this R matrix. I want you to see the differences here. R is called a reachability matrix. If rank is n, then it's a reachable for the discrete time system, time varying system. So basically B, this is Kf minus 1, Kf minus 1 to Kf. Here B is Kf minus 2. So these are reachability matrix involving state transition matrix 5. So that's the rank condition for R. R is a reachability matrix. But remember here we have W. This W is written as phi B, B phi. Okay, phi B, B phi, and add all these things add together. So this matrix is fully ranked. Okay. It's the same as the fully raw rank of the reachability matrix. So there are one-to-one relationship. This sign is called if and only if. Okay, if and only if. This W is non-singular or full rank. So reachability matrix R and discrete time controllability gradient, they are basically different. Okay. However, in continuous time system, they are the same. Okay. Observability, you check the observability gradient. This observability gradient. So this is called observability matrix gradient. This is called observability matrix. Observability matrix involving the phi. This is the summation, the phi C transpose, C transpose, and C phi. So that's again there's a one-to-one relationship, O and N. Okay, observability. So this. Going back here, reachability matrix is different to controllability matrix here. Be careful. So it's not controllability matrix. But however, in time varying case, we can use reachability by checking. That reminds me of Hoppus tests. So for all z in the complex rank, this is a fully low rank. This is a reachability condition. And this one is also true for this reachability matrix in here. Observability. So these are if and only if condition. Okay. So canonical decomposition is called Kalman decomposition. So we are going to do this one today, and hopefully we can go through all of them. Okay. So chapter 13 is the reading part. So for each of the linear time invariant system, that can be decomposed into controllable and observable subsystems, and C bar O, and C bar O bar. Okay. So input-output response is like controllable and observable. Okay, controllable and observable. That's what we really care. If the system is homogeneous response corresponding to the observability, so if you have in and out, input-output response corresponding to controllability and observability both. So if you only look at the in and out, homogeneous response corresponding to observability. Okay. That is also called when input is zero, so zero input response. Okay. So basically we need to understand the procedures. In MATLAB we have those codes that can do the job. Okay. So let's talk about controllable subspace. So first I want to understand, I want you to tell me why we come out A, X, B, U, this system, and there are some parts is not controllable and some parts are controllable. Why? That's the structure of the system. That's the structure of the system. Or because you didn't choose the state variable carefully. So what's the state variable? There is a very important thing, it's called minimum number of variables. Okay? Minimum number of variables. That can be used to describe the future state. Giving current state. Current state plus control signal. So that's very easy to understand. So you want to know the future, you based on currently what do you have. So it's basically you know the trend, then you know the control, then you can know what's next. Okay, what's next? So that's called a minimum number of variables. So number of x is minimum. What if it's not minimum? So there are many cases that this part was forgotten. It's not minimum. You used several more, you arbitrarily just for your convenience. Okay, you list those equations, you didn't cancel intermediate variables, you didn't use minimum number. That's the very important reason why we have an uncontrollable subspace. So in some cases, okay, can happen that you have another matrix here is n by n, E times here. That the E, of course, E is not zero, not singular. That you can put this side, okay? You can turn in the previous one. But there are cases because you didn't use a minimum number of variables, you end up having a E matrix here. And the determinant of E is zero. This type of system is called generalized LTV system, linear system. Okay. Okay, generalized. So if this is invertible, that's a different story. Okay. I'm saying that because you didn't use minimum number of variables, you could lead to having something E is not that. So sometimes this is also called a singular system. Okay, singular system. Sometimes it's also, some people it's called implicit system. Okay, implicit system. So it's just like you use something excessive. I want to squeeze away those unnecessary things. I only want something I need. This is called controllable and observable. That part is what I care about. Okay? But how you can get that one out is called decomposition. Okay? Decomposition. So you are going to see that we can have a controllable subspace and uncontrollable subspace. How we can divide that? How we can divide that? So I just explained to you why we have uncontrollable subspace. It's because one of the reasons you didn't use minimum number of variables. So then we try to squeeze you, okay? So that you have a minimum number. So let's recall that we are doing this. XTF is the integration of A T minus, so A is the LTI, okay? A is the LTI, remember. A is the LTI. And here is a sigma like tau, same. So this is the convolution notion. So this is a state transition matrix, okay? So if we check the df minus tau, so tau is 0 is like, sigma is 0, like tau is f, we swap them. So what we have is, do 0 to t, so it's like, this is tau, then this is tf minus tau. So this is very simple because we don't really have to do this. Because we know that f star t, star f is, star g is a g star, g star f. So meaning the convolution can commute. So this is basically showing that convolution can commute. Okay, so this one and this one can commute. Okay, this is a convolution can commute. If you denote u bar tau like this one, be careful. It's like one is you go time this way, and this one is minus t is go time flow that way. So be careful. So this and this, they have a different time axis. Okay, time axis is opposite. So, okay, so yes, you can write that way. So in the end, you can write this way. Okay, the reason we write this way is we try to introduce an operator theoretical thinking. Operator theoretic thinking, meaning there's a linear operator to operate on the u vector. This u is the input vector to the end state by this kind of linear operator. So therefore, this is a linear operator here. This is a linear operator. Operate on the u. Okay? So this operator's range is denoted as xc. So meaning you apply those u's, you can reach all those xc. Okay? If the xc is if the XC is fully the controllable subspace of this, there is all the distinctive eigenvalues spanned by the right eigenvector of the controllable modes. So if everything is controllable, that XC is my Rn, right? So you can go everywhere, but it may not be true because some of the eigenvectors are not, eigenvalues are not the corresponding controllable mode. So that's why we need to write, learning this model controllability. So this is so controllable modes, that depends on how you can put this lambda, and you put S, okay? Lambda S, Si, and you put lambda S minus A, and B. You do this Hottis test, okay? To the rank test. So we have learned last time, but those controllable modes, they may not have all of them controllable. You only have part of that. So the first all are controllable modes. The last are not controllable modes. So if anything in this controllable space, this XC, that space, okay? Remember, XC is a range of, XC is written as, XC is defined by the range of the operator, range of a linear operator, okay? Operator, that maps the U to the Y, okay? To the X, okay? To the X, and to the X. Let me go back and review this. So this range is basically is like you have a U, then it's operated by this thing. This thing is called T0 and TF. You have the E, A tau, and B. So, and this one will give me X, okay, will give me X. So all the X together, so it's X, all the X together, that X equals T0, TF, and again, EA, tau, B, U, T, equals D tau, okay? So we just say this is our, this is the set of XC defined by that. So that's easy to understand. If everything is, if you have a lambda 1, lambda n, lambda n, so everything is controllable, then the XC is nothing but Rn, right? You can control it anywhere, okay? So that's good. But in reality, it's not. In reality, you only have part of those modes. Part of those modes are controllable. But some of them are, the rest of n minus r are not controllable. Then it's question about, then what's the XC? So then XC is, of course, is a subset of, in this case, XC is a subset of Rn, okay? It's a subset of Rn. So we want to understand what's in the XC. So then we want to characterize it. So basically we are saying that for the R controllable modes, we have a corresponding right eigenvector, Vi, and linear combination of that, okay, combination of that. So linear combination, they span it. So this is called a span space for X1. So X1 will span a subspace of XC. So this is called controllable subspace. So here is the theorem. if the controllable subspace is spanned the columns of controllability matrix, which is controllability matrix is WC. Yeah, let's just use this one. But this is a kind of confusion about gradients. But it's okay. So you have n. So this is n by 1, n by m, n by m. So you have n, but the column, you have lots of column, okay? So this is not fully column, is less than n, less than n. So therefore, it doesn't matter, we just put this matrix range denoted as a controllable subspace. So XC, X sub C is a controllable subspace. That is totally dependent on the rank, okay, of the WC. So this can be proven by setting the x0 is 0 without losing so xf is written this way, we have seen it. Okay? We don't use tau anymore, just still using that one, it's still a linear operator. Okay, linear operator. So then according to the matrix exponential, you can expand it. This one expand it like this. So using Kelly-Hamilton to eliminate an, because everything above n will be 0. Okay? So therefore, what you have is the coefficient of gamma k. This is to the power of ak, so this is also k. This is also k here. Okay, so I'm sorry, you don't have to decay the power. Just say this gamma k is a function of this, okay? Function of this. So still you write this way, gamma k is a coefficient. Then your xtf, this way, times the u, and times the u. And because a and b, they are the constants, so you end up with this one. And this is dependent on the k, so you write it as a pk vector. Okay, so you end up with limited, not infinite anymore. You have a finite, summation of the matrix. So in other words, we can write something like this, xtf. Don't worry about what's inside the p, okay? So by writing this way, we already can see xtf is within xc, means xtf is in the range of this one, depending on the rank of this one. So that's if and only if part. So then only if part, do conversely, if it's already within the range, then it's a controllable model. So that's probably is. So in other words, we can say that controllable subspace is A invariant. That means if you have x is in the controllable subspace, so A times x is also in the controllable subspace. So, which means you have AXC is y equals AX, x, so y is also controllable. Okay? So, therefore, this is called A invariance, okay? Controllable subspace. Let's do how to do this decomposition. So we start with the controllable matrix. This is a controllable matrix. Of course, the rank is not the same. It's less than n. It's less than n. If it is n, then it's all controllable. There's no uncontrollable subspace. All controllable subspace C bar is, in this case, for now, C is R, and then C bar is now. Okay. C bar is now. This is nothing in there. Okay, nothing in there. So the question is how we can see it. So that's the basis change. Okay, so after the basis change, we hope the first NC states are all controllable, the rest of them are not controllable. So we pick NC linearly independent columns of WC. Then we form Q1 matrix. Okay, so NC is the number of controllable modes. Okay, controllable modes. Linearly independent columns of WC. Okay, so of course this is the same thing. The range of Q1 here is XC. So then Q2 is the rest NC plus 1 until N. So this is, you know, that Q1 and 2. So then Q1 to QNC is number of controllable modes, and these are the rest of non-controllable. You put together is a basis for Rn. Alright, so we define Q1, Q2 stacked together. Okay, of course it's n by n, and we use inverse is p, and write this inverse as P1, P2. Okay, so straightforward calculation give us P inverse is PQ left. The reason is you have P1, P2, Q1, Q2. So that means you have this relationship. Okay? This relationship. Is this confusing? Let me do this. So you have Q, constructed a Q. Then you do its inverse. And you partition it to two parts. Okay? Then PP inverse will be I. P inverse already noted as Q. So then this is a low rank product, rank 1 product. So then you get this one, and here you have these equations. So in other words, we should have P1, Q1 is I, P1, Q2 is 0. It's like they remind you some sort of P2, Q2 is I. So something like orthogonal property. So then we put AQ in there, A matrix in there. Okay. Again, you have AQ1 and QCN, so these are the vectors. Because we have known that the controllable subspace is A invariant, so you put A in here, it's also within the XC. So AQL, any of these, you have the linear combination of the rest of them. Okay. Is Q1 alpha L. So you do every column, you end up with gamma, you obtain the gamma. Okay. So then you do the transform. Okay. What do we have? We need an example to go through. So we need to put X bar. So X bar is written as PX. Okay, P is the Q inverse. Okay, Q inverse is P. Okay, so let me write down. I got confused. Let me do this. So we have X is, we do a QX bar, and Q inverse is P. So I write X bar is PX. So this is nothing, just a notation. But when you transform, you write in X dot, okay? X bar dot is PAQ. It's a PAQ X bar, okay? Remember, Q is P inverse, Q is P inverse. P is Q inverse. So it's basically PA, P inverse, and PB, and C, P inverse X, and you have P. So D didn't change. D didn't change. So what PAQ will look like? So let's focus on that. Okay. So PAQ, remember, of partition of P1, A1, A, PQ. Remember with P1, Q1, P2, Q2, they are all I. Others are 0, so we are writing this way. So that one. Okay. So EQ1, Q gamma, so then P2, Q1 is 0. Okay. P2, Q1 is 0, so 0. Then PAQ will have a structure like this, So we comfortably put this one in 0, but this one is not yet. So in the end, we made in the X bar column, we made our A matrix into upper triangular form. So AC is the controllable state matrix, and AC bar is uncontrollable. And A12 is PAQ2. P1AQ2. Okay, this one, A12. And so input signal is P1B, P2B, and P1B actually it should be P2B should be P2B. The P2B should be 0 to me. Okay? Yeah, this should be 0 because there's nothing there. Okay, there's nothing there. Because you have P2Q1B bar. Okay. So then we know this is 0. We know this is 0. You want to have BC there. So this is the input. But for output, you cannot say much because both of these will be staying here. C and CC bar are the same. So the state will partition is XC bar, okay? XC and XC bar. And then the overall system is upper triangular form, so you should take a look. By doing the partition, doing the transformation, we can make it a partition of the transformed state in 2 parts, XC, C bar. So AC bar here. And so you have BC and you have CC bar and A12. And all this standard form so is called controllable canonic decomposition. And you need to make sure these 2 things must be 0. This is 0. So that's it. So by doing that, you may feel like, how I can do this? It looks very complicated. But the AC, BC is controllable. Okay? But AB is not. AB is not. So original system is AX plus B, right? Is AB controllable? The answer is no. But it's only AC, BC is. Okay? AC, BC, yes. After I did the partition, so the partition is written in this way. This partition. So you may wonder how I can come out this P matrix here. How can I find out P matrix? Okay, I'm going to do some of that in a minute. So we know that the AC, BC for that subsystem is controllable, AC, BC. And if we do input output, you are going to see input output. So I want to remind you again, the size of A and and size of AC, they are different. Size AC is small. It's a square matrix, but smaller. So, but in the end, this will give the same GFS. In other words, although you have uncontrollable parts in there, from in and out point of view, this system, this subsystem, okay, AC, BC, CC, U, this has the same in and out, input-output response as the original bigger system. While the original bigger system, the reason you had that kind of bigger system, the reason is you didn't use the minimum number of states to do this steady space development. That makes you to have the work left to further refine it into two parts, controllable and observable. Controllable and uncontrollable parts. So this kind of decomposition is unique up to a basis change. So you may have a basis change, have a non-invertible controllable, non-invertible, it's an invertible, invertible matrix. So this is not, it's unique, but it's actually not unique. The reason is you can always place invertible determinant m is not 0. You can put it in here. You can always put it in here. So in other words, we have seen the controllable subspace only affects the in and out of response. So you do the basis change for the change in the representation of the controllable state. And for the rest of those spaces, uncontrollable, they complement with controllable subspace. Then add together is the original space. I'm not sure you are clear about this. I told you controllability may not be always guaranteed for each of the states you choose to describe the system, because the choice of the states to describe the system might not be the minimum number. So because of lack of experience, or for just lazy, so actually choose more than actually needed. Then some of those are not controllable. You cannot reach there anywhere. So you have to partition that. So let me go out and show you. Yeah, there's a control. There's a control BF, CTR BF. Okay, they are going to give you controllability staircase form. So that is exactly the AC bar, and 0 A12. Then you have a XC bar, DDT equals this one. This is XC bar plus B1, B2. Okay. So what you give the original systems ABC, okay? They are going to give you back A bar, B bar, C bar, and T and K. And especially that T matrix is interesting. So they will give you directly this T. So this is A bar. So this is AC bar. So this is called staircase for lower triangular, but people also do upper triangular. So this is just transverse. Okay. So we use the upper triangular. So the same, okay? A bar, B bar, C bar, okay? These are the transformed. B is transformed to B, C is transformed to C. And they gave you the T also, I gave you the T, okay? And from input-output point of view, this transfer function metrics are the same, okay? So that's A bar becomes like this. B bar, there's one part is 0, so it's C bar. So there's one variable not controllable. T bar, I think the T, the K will kind of indicator of your, let me see. The K will give you an idea about which variable is not controllable. Each entry of K represents the number of controllable states factored out during each step of the transformation matrix calculation. So non-zero element K indicates how many iterations are necessary to calculate this capital T. So you do the controllable portion of the A bar. Okay. So you can play with this one to help you to do all this transformation like we have seen here. So we have seen here. So you may wonder where is the T matrix? So the T matrix is the P, okay? It's the P. Well, we are going to check. So looks like we only did the partitioning of two parts for state space for controllable and uncontrollable. But you have a parallel one, it's called observable, canonical decomposition. People say this is a dual problem for observability and controllability. Remember, let me refresh your memory. If you have a system, okay, A, B, C, matrix, what is a dual system? You need a minus sign here. So that's our dual system. So that's why you call observability, controllability a dual problem, because of the dual system concept. So let's see how we can do that. So again, we define unobservable subspace. So only focus on A and C. Initial conditions that produce a zero output. Okay. So it's not observable. It's not observable. Remember that. So of course it's a subspace. So here we need to revisit what does it mean about observable. Because observable, you can always add an initial condition that produces a zero output. Okay? So you tune that initial condition then until you see the output is 0. So observable initial condition need to unobservable subspace, okay, need to contain that. Let's see more clearly what do we mean about So it's a null space of the observability matrix. So null space means you got a 0, okay, M0 here. Null space is X, L bar. Those are not observable subspace. So in other words, say for example, X, this unobservable subspace is also a invariant meaning. So if you have something not observable, then A times X, any vector generated is also not observable. So which is quite obvious. Now let's talk about dimension. So this is the rank. This is the rank of M0. It's unobservable. And this is observable Gramian, the matrix, okay, the rank. N minus this one is this thing N. So then we can pick N minus N O bar, this number of uncontrollable modes, or unobservable modes, linearly independent rows, choosing from that, having orthogonal complement of X bar, forming this P1 matrix, okay, forming this P1 matrix. So N minus N O bar, that's number of observable modes. So then we pick any N O bar row vector to form a basis that you can choose arbitrarily you want, just to make sure it's a basis of Rn. In other words, you can make this fully ranked by choosing the free N O bar vectors. So in other words, the P2 here can be choosing any way you like. Just make P1, P2 a fully ranked. Can be a basis, okay, of Rn. So in that way, we can do this P matrix of two parts. We write it in this way. The transformed part is observability is a lower triangular part. And remember, corresponding to 0 here, this one is 0. Okay, this one is 0. So in other words, X O bar, this state is not observable initial condition. So this is called observable canonical form. So then I want to highlight these 2 zeros for you. You got to see these 2 zeros. So this is also called observable staircase form. Okay, staircase form. Don't feel very surprised about things are different, because we are writing observable up. This is down. So that's why you have this. If you swap them, then you will go into an upper triangle, upper block triangle. This is a lower block triangle. So observable canonical decomposition is like this. So let me go to here. Let me show you the command. So this is called controllability staircase form. You can do observability staircase form as well. Okay. On the other hand, because this is dual, you can imagine that you can put this A transpose minus A transpose, B transpose, C transpose, and B in here. What you get is observability. So that's why we don't see this is CTRBF. CTRB is a controllability matrix. CTRB is something like C over here. Okay. And you have observability these are the OB metrics. But people may ask why I don't see OBSVF, it's called observability staircase form. I personally believe you don't really need this OBSVF. I don't think you really need it. Because why? You can put a controllable staircase by putting A minus A transpose C transpose B there, you will be able to get the set. Now I suggest you play with this command and control form, staircase form, and using this one, and compare the results. Okay, I suggest you do that. My conjecture is they will be the same. In other words, this command doesn't need to exist. Okay, doesn't need. Okay. Prove my conjecture by playing this. So we have a few slides left, and let's see what do we have. So, canonical form. So there are codes you can do this decomposition. And again, this is, oh yeah, this is. So we have observability. So A0, C0 observable. Then this is G of S. Is unique up to some basis change in subspace. So that is a canonical decomposition of controllable, uncontrollable, observable, unobservable. So I'm hoping that we are going to see this canonical decomposition in the full picture about this four. So this is a controllable canonical form. Okay. So G of S is only determined by the controllable subspace. Same is true for observable canonical decomposition. Okay. Okay. All right. So now you can imagine that canonical decomposition actually has more than that. So we have four different subspaces. C, O, C, O bar, C bar O, and C bar O bar. Okay, C bar O bar. Okay. So for the input-output response, so you only take care of this subspace, that structure. And the homogeneous response only corresponding to observable form, meaning zero input response. So we do controllable decomposition, then we apply observable decomposition to the controllable subsystem. So then we apply the observable decomposition to the uncontrollable subsystem. Okay. So So let's start by controllable decomposition, then we do observable decomposition to the controllable subspaces. So that's the idea, okay, that's the idea. So we don't care about XC, we don't do anything here, okay, we don't do anything here. But we do the controllable subspace, then check the observable part and unobservable part, okay? So then we just, we know that we originally have AC, this is AC, This is AC, this is 0, AC bar, this is A12, okay? So remember, our original form actually is this one. I hope I'm going to write down this one so we don't forget. Okay, so AC bar A12 0, and here is a BC bar. Okay, in fact, Y is CC bar. X plus du, okay? So then we know that this thing must be 0. So this one is 0. 0, okay? Now, we need to study this one and this one. We know that in a controllable subspace, okay, there are another two parts, okay? One is controllable, but controllable and observable, and controllable and not observable. So we need to do this partition. So this partition is like XC O bar, XC O bar, XC O. So this is my XC. Okay, this is my XC. So I need this partition. Okay. So the idea is we talk about controllable and uncontrollable. Then we just zoom in this part, okay? And this one. This is my original AC, okay? AC, okay? AC. So we need to partition it into two parts, okay? All right, so, okay. So it turns out that by doing that, the observability canonic form is a lower block, lower triangular form, right, like that. So it's no surprise we have this. Okay, and remember, we didn't do anything on this, only make this BC two parts. One is observable part, one is unobservable part. So it is very important to remember here. This originally is called CC, okay? They do two parts, one is CO, one is CO bar. The CO bar must be 0, okay, must be 0. So these things you cannot change, it has to be 0. Otherwise, it's not a canonic decomposition. So be careful. So again, XCO bar form XC, okay, XCO bar. This is XC bar. So that is the format for this decomposition. Then for this one, I also do uncontrollable, unobservable and observable part. So that's the next step. So observable decomposition to uncontrollable states. Okay, so this is a XC bar, also with O and O bar. So then you end up with this is lower triangle block partition matrix. Okay, back in observable canonic form. So then again, you didn't do anything here. This is still 0. Okay, but there is C bar, O bar here. That must be 0. So overall speaking, we have done our canonic decomposition. Okay, canonic decomposition. This canonic decomposition will have very important structures here. So this is all zero matrix. So if these are not 0, then it's wrong. For the theorem part is, I have 4 parts, okay? I have 4 parts. I partition the state space in 4 parts, 4 subspaces. CO, CO bar, C bar O, C bar O bar. Okay? So finally, you'll see what is really left is both controllable and observable is this subspace. CO, ECO, CCO. So I hope you can recognize where they are. Okay? ACO, okay, BCO, and XCO. Okay, CCO. Okay, this one. So these 3 is forming both controllable and observable subspace, and the input-output relationship is only linked to these 3 matrices. Okay, and those decompositions are unique up to a basis change within the subspace. Okay, those dimensions of the blocks is not going to change if you do similarity transformation, because that's a geometric inherent property of that state space of original system. Okay, so those modes, controllable, uncontrollable, observable, unobservable modes will never change. Okay, no matter how you do a coordinate transformation. So the properties of the modes is not changed, okay, by doing this partition. So I hope you see this picture now. So you have a system like this. So you have 0, 0, 0 here. So this is a 4 subspace. So this is 0, 0 here, 0, 0. So you see this is called Kalman decomposition, but really what you see is from here. So this is from input output is directly connected like this. So it's observable from here to here. It's controllable from here to here, but not observable. And so this is not observable, not controllable. I hope this picture is so clear to everyone. So it's very interesting. I'm going to tell you something. Because you can observe, you can feed those observations here. You can control, then you can control here. So you can observe. Okay, you can observe. You can feed in here. You can control that. Okay. So what I'm trying to say here is, if you have a mode that is not controllable, okay, not controllable, and that mode itself is unstable. We are going to talk about this one later. So this is called inherently uncontrollable, unstable mode within here. It's going to blow up, and you don't have a grip on it because it's not controlled. So that is actually a fundamental question about a concept of stabilizability. Okay? So it's uncontrollable subspace. Okay? The uncontrollable subspace. Then you also have a matrix is A uncontrollable. And if this A is C and its eigenvalue, okay, and its real part greater than 0, that means that mode is inherently growing and unstable, and you cannot do anything about it because it's not controlled. No matter what you do, because uncontrollable meaning you have a B, C, and B, C bar. This B, C bar is 0, okay? Times U. No matter what you control you put in, you are not going to change it. Make sense? So There are a lot of places they call, oh, this is not stabilizable, meaning the open loop, the system, uncontrollable subspace is unstable. Okay. So we are going to finish here, and in summary, you are given this one, you can do input output by doing this, but actually you also can do this because you only care about control. They are the same. They are the same. So in other words, no matter what kind of transformation or coordinate transformation, you do a coordinate transformation, the input output will not be changed. In and out will not be changed. So that's why the state space is also called internal representation. Internal representation. But for the in and out, it's the same, but internally, you can interpret in many different ways because you can do X is P, Z. You do a coordinate transformation. You can do no matter what you do. But you are not going to change in and out property. So everything happens is internal. So it's intrinsic. So by understanding this canonical decomposition, we have a pretty good idea about the structure property of linear system. So this is a major contribution by Kalman. We did that kind of. So everything is so clear cut. So we have very good good insight about linear multivariable control. Okay. So same thing can be said about subsystem essence of the dynamic system. So now they are using this word. So if you do this common decomposition, you squeeze all other things away, you only keep COs, ACO, BCO, those both controllable, both observable there, the subspace, then you will lead to a minimum order description of the transfer function. That's so true. So true. Okay. So you got A, B, C, D, then you do some decomposition or transformation. No matter what you do, you will end up with the same transfer function using the same A, B, C, D. Okay? So it didn't change. So in and out didn't change. Inside, internal representation can be infinitely many. So that's what we have learned about Kalman decomposition. And next time, we're going to learn something very interesting, very deep. We already know that giving G of S in and out, okay, in and out, internal representation will be infinitely many, okay, infinitely many. So then we find state variable description. How we can find out a state variable description? There are so many different types of description. There are infinitely many, but some of them are useful. Some of them are very useful, convenient. Say like controllable canonic form, observable canonic form, and so on and so forth. This cool thing is, so let me do this. Okay. So this is from in and out, okay? Then you know that for state space representation leading to this one, no matter how you do the transformation here, you will lead unique. This is invariant G of S. But on the other hand, if you are giving G of S, Okay? Go this direction. How would you find out a state space representation for that? This is a question called realization. Okay, realization. So we're going to cover realization next week. Okay, you can stop here, and then next Monday we are going to do a study session again. Thank you. All right. So in summary, today we just did Kalman decomposition. I hope you feel more comfortable when you read through the text. Pretty well written in this. Okay. Bye bye.